Last class we are writing the Boyle's law, which says that PV is constant. Well, you should also remember how the plot for this one looks like. If you have some sample, and on one axis you have pressure, and the other one you have volume, this condition, PV equal constant, gives you a line that looks more or less like that. This is the line of PV equal constant. If you have the other law, Charles' law, that says that volume is proportional to the temperature, or you can also say that volume over temperature is constant. You can plot this one as volume as a function of temperature. And the plot will look something like that. Of course, this one goes here infinity, but this one stops here. Why this one stops? Why there is no continuation? Because there is equation for gas, and there is no gas anymore here. There is liquid. In low temperatures, the gas becomes liquid. But if we can come down to this point, what would be the point, the temperature? That would be minus 273 degrees Celsius. And that's how the Kelvin, 0 Kelvin is found, usually by extrapolation of this plot. And turns out that this is for one gas, but you can do it for another gas. And turns out the plot look kind of similar, but the extrapolation again gives the same point. Then we learned the ideal gas law. That says PV equal nRT. Now I have to know, did you study in high school? All of you. Very good. Because it means we don't have to spend time how to solve exercises using this law, because it's so simple to find the pressure or find the temperature when you have the other things. But what I want to study with you today real gas laws, not ideal gas. And before we go there, the last thing for the ideal gas would be the density. Density, well, usually by the letter D, is given as a mass over the volume. You can write this one as number of moles multiplied by the molar mass divided by the volume. And you see that from this equation, N divided by V is nothing else like P divided by RT. So you can use it for NV here, getting P M divided by RT. Now, this is a constant, M, molar mass, you can consider also a constant for every gas. So you see that density not only depends on mass and volume, but you can also find it as a function of pressure and temperature, which is, nothing very complicated. Just another way of calculating the same things from different data. So this is useful to combine different laws together. Another thing, this molar mass, so before I go to the real gases, this molar mass is a mass of 1 mole. Well, but we should define what is 1 mole. In 1 mole, it means amount of molecules equal to 6.023 times 10 to the power 23. This number is called Avogadro constant. And usually is denoted by the large letter Na. How this was found? Well, for today, it is defined that you take 12 grams of carbon atoms. Well, to be more precise, you have to take the isotope carbon-12. And the number of atoms gives you this Avogadro constant. Good. Now we go to the real gases laws. We have this law, which is the ideal gas law. And how it was found? Well, very simple. People just took some volume of gas and they were changing the volume by pushing one of the walls, getting smaller and measuring the pressure. Pushing, measuring the pressure. And by doing this, for every volume, they found 1 point on the curve. something like this. And they found, okay, if we calculate P times V, it's not changing, it's constant. But turned out later that this one is true for small pressures. Turns out that if you go to high pressures, it's not more any true. Not true anymore. Well, if it's not true anymore, then what is true? And people try to do the mathematically correct thing. They said, if this is not true, if this is not constant, I call this constant alpha here, then it must be constant alpha plus some small correction. Now, how to represent the correction? It's true that this one is correct when the pressure is small. So for the high pressure, there must be corrections. Okay, let's try to put the corrections in the form beta times pressure. In fact, you can define a mathematically correct procedure, and now we are going to do this before following with this. Expansion of a function in a Taylor series. Did you study Taylor series in high school? Probably not. Okay, not a problem. What I want to say is that there is a proof that if you take any function of x, no, I cancel my word any function, but for many functions it's true. If you take a function of x, then you can find a different representation of this function. And the representation will go like that. This is function at the point 0 plus derivative of the function calculated at the x equals 0 multiplied by x plus second derivative of the function calculated at the point x equals 0 multiplied by x squared divided by 2 plus the third derivative of the function calculated at the point x equals 0 times x to the third power, and here 6, plus f to the fourth one, divided by 24, plus infinitely many terms. Now you can write it very shortly, saying that this is an infinite series when the summation starts from 0 and goes to infinity. Now, in the denominator, there would be k factorial. As you see, 1, 2, 6, 24, this is the factorial. And in the numerator, we will have the k derivative of a given function calculated at the point x equals 0. And everything is multiplied by x to the power k. That looks very strange probably for you, but this is usual Taylor series expansion for any function. And the question is that this is an infinite series. Infinite series can converge or can diverge. So it's always defined, but just not always converging. Turns out that for many functions that we are studying, this is converging very nicely. Let's do example. Example would be e to the power x. Okay, I'm going to find the Taylor expansion for the function e to the power x. Well, then I have just to follow this prescription. So let's calculate first the f k derivative of x. But it means that this is function e to the x k derivative. But derivation of this one is kind of boring. It's just ex. So now if I calculate the f k of x calculated at the point L equals 0, that would be e to the power 0. That will give me 1. So it means that this term is 1 for any k. If this is true, then I'm finding the expansion for this function is just k equals 0 to infinity. And here would be just x to the power k factorial. Good. You can find expansion of the function sine x. For the sine x, we know that we are going to have infinite series, k starting from 0 to infinity. And now we have to calculate the sine x k derivative. What is it equal? Well, simply, when k is equal to 0, it will be sine x. When k is equal to 1, that will be cosine x. When k is equal to 2, that would be minus sine x. When k is equal to 3, that would be equal to minus cosine x. And you see that k equal 4, it comes back here. 5, 6, 7, 8, 9, 10, 11, and so on, and so on, and so on. So now we have to evaluate the value of the derivative at the point x equals 0. X equals 0, sine at x equals 0. And what we are finding here that this one, sine at x equals 0, is just 0. Cosine is 1. This one is equal 0, and this one is equal minus 1. Then the first thing we see that 0, 4, 8, 2, 6, 10 are gone because they have 0 coefficients. The only way this retained is 1, 3, 5, 7, 9, 11. Only the odd terms in this summation. Okay, so we have to modify this. So the summation starts from 1, 3, 5, and so on. Then it will be 1 minus 1, 1 minus 1, 1 minus 1. How to put this one? Well, the easiest way of representing this one would be minus 1 here to the power k minus 1 divided by 2. Check if it works. K minus 1 would be 0 divided by 2 is 0, minus 1 to the power 0 gives me 1, correct. 3 minus 1 is 2, 2 divided by 2 is 1, minus 1 to the power 1 is minus 1, correct. So this one works. Then we have k factorial here, and we have x to the power k. Good. Some people are representing this one in a bit different form. they start from, I put it here, L. L equals 0 to infinity, and what they just do, they said minus 1 to the power L, x to the power 2L plus 1, and here is 2L plus 1 factorial. These are the same if you think about it longer. Good. Well, if you learn about these sine functions a bit more, finally you find that this is in fact definition of the sine function. That sine function is defined through this series, through the infinite series. And the exponent in fact is defined through this series. People didn't know what it is, and people didn't know what this one is, but they were meeting this series very often in the calculations, and they just gave them the name exponent and gave the name sine. That's how they were created. But the important part is that many functions can be expanded as a constant plus and this is called power series. Why I'm writing here dots? Are these terms not important? When you think about that longer, you see that when x is very, very small, then the next terms are really not important. And the reason for this is that x is maybe small, but x squared is really small. And next one, x cubed, would be very, very, very small. So for small x, this is a correct description. Good. So what we are doing here, we're just finding the power expansion of our P times V product that is not constant anymore, but has corrections. And now I call it B1, B2 P squared, plus B3 P cubed, plus infinitely many of them. This is called virial expansion in physics. And the virial expansion can be done not only in the pressure, but as you see, pressure would be from this equation approximately constant divided by V. Another way of putting the virial expansion would be writing it in this form. Alpha plus gamma 1 over V plus gamma 2 over V squared plus gamma 3 over V cubed plus and in fact, since the experiment usually is changing pressure and measuring volume, not opposite, not changing volume and measuring pressure, rather changing pressure and measuring the change in volume, this form is the preferred form for the virial expansion. Now somebody can ask, how big are these numbers? And why there is no temperature there? Well, I answered the second question first. Turns out that this alpha depends on temperature. This one depends on temperature. This one is a function of temperature. And here the same for these ones. It's a function of temperature. Okay, and I give you the values of these few constants at different temperature for helium. I know these are new things for you, and the mathematics that you didn't learn, but probably you will learn in this year anyway. So you had just introduction. Since we have to use it to explain the results in the book. Okay, in your book, this equation just appears on the page. This is equation 31 on page 152. And they give no explanation how this is derived. So I'm just showing you that from mathematical point of view, it's nothing complicated. It's just the Taylor expansion of our product. Now let us discuss for a moment these coefficients. Then you will see that writing dots here makes sense. You can read about this Taylor series in any textbook on mathematics. Good. We have helium. And let us say what are the A, gamma 1, gamma 2, maybe gamma 3. I don't remember how much I have with me. So we are going to write temperature here. I said they depend on temperature. Let's see how much they depend on the temperature. Let's write temperature, and the temperature will be in degrees of Celsius. And then we are going to write alpha. And of course the alpha must be given in the liters times atmosphere. Then we are going to write beta 1 in the units of liters times atmosphere, and here would be square, and beta 2 in the liter cube times atmosphere. And we are going to have different temperatures. 100 degrees, 20, 0, minus 100, 3, minus 182, minus 216. The first term, 30.6, 24.1, 22.4, 13.9, 7.4, 4.6. And if you look a bit longer, you probably recognize that this, in fact, it looks like molar volume. At 0 temperature, 22.4, in the 20 degrees, 24.1. So you see that this thing, this alpha, is really changing with the temperature, and it's kind of large. Now the first correction. So this is the ideal law. Ideal gas law. Now we have the first correction term, and we see that the first correction term is already much smaller. And second correction term is much, much smaller. Good. So now, there is a very important issue. If somebody is going to use the ideal gas law for helium, and the pressure will be small or volume will be large, these corrections will make very, very small contribution. But opposite, when the pressure will be large or when the volume will be very small, then these numbers can give you like 5 to 10% error even. Well, this first value, this alpha, you can find what is the dependence on temperature from this data. And you find that dependence on temperature is 0.082054 multiplied by the temperature plus 273.15 liter times atmosphere divided by mole. And this is nothing else than R, and that's how it was found. We are always quietly assuming here that everything happens for 1 mole of gas. Good, good, good. So we know that this one is true at low pressures. What about high pressures? We can write the following plot. So for now we are studying just the equation PV equal constant. Now let us study the equation, the ideal gas equation. Here would be pressure. That's what we are going to change. And on this axis, there would be something strange. There would be PV divided by RT. You remember that we have PV equal nRT, but since we are working for 1 mole, N is equal 1, we have PV equal RT. So we have this equation for the ideal gas. So we have also PV divided by RT equal 1. So when I want to plot PV equal RT as a function of pressure, then there should be much to plot. Just put 1 everywhere, right? It doesn't depend on pressure. It doesn't depend on anything. But that's true for the ideal gas. Now I'm going to plot this PV RT for some real gases. And you see what it will be. The plot will be done for N2, so for the real gas, for the nitrogen, at 3 different temperatures. So we start with the temperature 0. If the temperature is 0, it really starts from here, then goes slowly down with pressure. When the temperature is minus 100, it again starts here It goes down all the time. And finally, for the high temperatures, the plot looks like that. Which kind of explains why people find the ideal law. Because looks at the low pressures, all of them go to 1. But the pressure must be very large. When I say very large, I mean that it must be measured in megapascals to observe these strange effects. How big is this plot? Turns out that not so big. Here would be around 1.1. Here would be around 0.7. And of course, I should also tell how many. 10 megapascal, here would be 5 megapascal. So you see that there are temperatures when the real gases kind of behave similar to ideal gas. But there are temperatures when they behave very differently, especially in low temperatures before liquidification. Let's do one more plot and let's have a break. Another plot will give exactly the same thing. Again, PV over RT for 1 mole of different gases. There would be oxygen, hydrogen, and CO at 273 Kelvin. So at minus 100 Celsius. So again, we have this point with 1, where all the curves starts. And then we are plotting 3 different curves. And we know that the ideal gas wouldn't just change. That would be ideal gas. What happens? Let's start with hydrogen. Turns out that hydrogen is always in the positive departure from the ideal gas law. Turns out that the O2 first goes down and then goes up. And the most interesting is CO. CO goes down very much up to this point. Then it's a straight line. What happened here? Well, let's try to think what happens. This is pressure. You change the pressure, simply, here it was gas. Here it became liquid. Well, in the gas, P times V is becoming constant. It has this shape. But for the liquid, the volume will be not changing anymore. So only the pressure going up, so it will be a straight line for the growing pressures. Okay, so the important message from this first half of the class is that ideal gas law has errors. And when you go to high pressure, these errors are big. Okay. We are going to continue after the break. What time is it now? discuss these plots a bit more, people define something what they call Z, compression factor. That is given as the volume of the real gas to the volume of the ideal gas. And when the compression factor is very close to 1, they say that the gas behaves like ideal gas. But when it's larger or smaller, they say that there is a departure from ideal gas. Good. So now we have to discuss something else. If there is an ideal gas law, does it mean that there also exist real gas laws? Something what connects pressure, temperature, volume for real gases. And turns out that yes, such things exist. And we already wrote the virial equation that was in the form of alpha plus beta 1 pressure, beta 2 pressure square, beta 3 pressure to the cube. And we said that we also can be expressed in another form, gamma 1 over V, gamma 2 over V square plus gamma 3 over V 3 is gamma. Somebody doesn't have experience to write gamma, you should write it like that. Plus the higher terms. We said that this virial equation is usually used to the but usually not in this form. What people do, they take alpha out. So the equation looks like that. PV equal, they take alpha out and they also found that alpha was equal to RT. So that equation looks RT one plus and these coefficients are usually written by the letters B. Prime for pressure and without prime for volume. Okay, and this is what we are going to refer to as a virial equation. Now you see that there are two of them. One depends on pressures, one depends on volumes. Usually this one is used. So when somebody says virial equation, usually means this equation. So now B1, B2, B3, these are called virial coefficients. And we have that B1 is larger than B2, is larger than B3, and so on. So this series very fast converge. Now, since they can be positive and negative, we rather should say that the absolute value of them is getting smaller and smaller. There is one more issue that we want to discuss. We know that the ideal gas equation says PV equal RT. I'm not putting here N because everything happens for 1 mole of gas. Okay, we are just discussing everything for 1 mole of gas. But if you are not discussing for 1 mole, then it should be N here. Okay, so now when the ideal gas equation is going to be close to this equation. Clearly, they would be closest if B1 is equal to 0. Now we know that B1, in fact, is a function of temperature. And it's changing with temperature. Usually, for small temperatures, B1 is negative. For large temperatures, B is positive. So there is a temperature when the B1 is equal to 0. Every gas has this temperature. This is a very special temperature called Boyle temperature. Unfortunately, I didn't bring any examples. But anyway, there is a temperature when the B1 is exactly equal to 0. What is the significance of this finding? You remember we were plotting before function of PV over RT. And we said that for ideal gas, we are expecting line. At the Boyle temperature, in this temperature, the ideal gas equation for some time goes very close to that line. So there is long range of pressures when our real gas behaves like ideal gas. And the reason is that the largest correction is vanishing at this temperature. So for this one we have T equal TB, the Boyle temperature. Good. Now, how to find B1, B2, B3? Turns out that you can get them from experiment or you can calculate them. Now many programs can calculate this one. This one is still difficult to be calculated. But it's kind of easy to get them from experiment. Now, to find this one, people have to know quantum mechanics very well. So maybe this one happened 60, 70 years ago. But people were dealing with gases for a long, long time before. And except for the virial equation that we just defined, and that is the correct physical description of real gases, there are some other description of real gases. They are not physically correct. They give the same results, but they are not physically correct. The physics is wrong inside. And I give you some of these equations. The most important, really the most important is van der Waals equation. And this van der Waals equation says that instead of using PV, use this one, P plus Of course, I don't have to say that everything happens for 1 mole. You have van der Waals equation that instead of using PV, you have some correction to pressure, you have some correction to volume. These A and B are called van der Waals parameters. And this equation is working much better than the ideal gas equation, but worse than the virial equation. And people like to use it in the technique, in the engineering. This is favorite engineering equation. This is favorite physicist equation. Okay, this equation was found kind of long time ago, 1873. And there was no quantum mechanics at the time. People didn't know what are really the forces between molecules. And it was, for a long time it was believed it's correct, but finally it was found out not very correct. There is not much physics inside this. There are many other equations. There was an equation where it's called Berthelot equation. Saying P plus A V square T V minus B equal RT. Or Dieterici equation. Saying that P multiplied by V minus B equals RT exponent minus A R T V. All of them describe the behavior of the real gas. But before using it, you have to find what A and B is. So you have to measure the pressure and volume temperature for your gas at some temperatures. And after it's measured, then you can make a collection of chalk at the end of the class. Okay, so you can measure at few temperatures and few pressures and volumes what is the A and B, find them and then use for any range of temperatures. Now, this one was pretty good. This one was much better. And this one was much, much better. But nobody's using these two. And the reason for this is that they are too complicated to be used. People prefer something simple even if there is no physics inside. But to be honest, recently this is used only in engineering. Almost all other real scientific papers are using this equation for the real gases. Good, good, good. We finish this part. One more correction here. Since we are always talking about 1 mole of gas, then I can put here just the small letter m, meaning molar volume. Now these equations would be correct for any number of moles. M and m. So we defined the gas theory from the phenomenological side. Now we are going to define it from the statistical side. So what we are going to do, we are going to take huge box of the volume V and n particles inside. So we have volume, we have number of particles. And now we try to use the properties of every particle. So every particle has a mass, has position, and has velocity. You tell me that's not everything. If this is real gas, then every particle interacts with other particles. So it also has potential energy of interaction, electric repulsion. True. But for the ideal gas, you do very strong assumption which says no interaction. Somebody says, but this is not real. No interactions at all? And the answer is yes, no interactions at all. And this is also the answer for the question why the ideal gas model is not so good. Because in the real gas, you have interactions. The particles are going to bump into each other, and when they bump, they kind of do it slowly, change direction, and go away. In the ideal gas, you just assume that you have two balls coming together, hitting and going away without changing the total energy. But in the real collision, when you have, for example, N2 and N2 coming and hitting each other, one of them starts rotating very much, going away, and the other one rotating other direction. When they hit each other, one of them can vibrate very fast after. So you see that in the real collision is something more complicated than just collision of the ideal gas molecules. This is called hard sphere collisions. There is another story. In the hard sphere collision, the collision doesn't last. It's extremely short in time. But in the real gas, after collision, the molecules for a moment are together and then they separate. They make a complex. They make a complex molecule and then they separate. So this is not a very realistic model, but still we are going to use it to find some other things. So we know that every particle has a mass, has position, and has a velocity. And that's virtually everything what we know about our samples. Now, if you are able to say what is the position and velocity and mass of every particle here and keep track of history of the system, then you know everything. Then you have all possible data about your system. But that's too many. This is 10 to the 23 particles. This is a huge number. This is a very huge number, and there is, let's just calculate. Let's say that every particle can be 0 or 1 state. So you need 1 bit to remember every particle. If you need 1 bit per particle, it means you need you need 2 to the power 10 I don't have time for this now. But anyway, that's a very big number. So what I wanted to do, I wanted to calculate how big disk in the computer I need for storing this information. But it would be much larger than any disk that are sold now, just for this one small system. And that would be only in one short time moment. Then you have to another story in the next time moment, and so on and so on. Anyway, you have this large system, you have the particle with mass, positions, and velocities. And now we know that this system has some pressure, has some temperature, has some volume, has some mass, and so on and so on and so on. Some of the things are easy to find. For example, you know that the mass of the system is the summation 1 to the number of particles of all masses in the system. This still requires knowing all the masses. This is kind of difficult. But you can say in other words, that would be similar if you do the number of particles multiplied by the average mass. Okay, this is better. So we found that the mass would be kind of easy to find. I put here M. Volume, this probably would be difficult to find from the volume of single particle because the particle is here, next one is here, and between them there is a lot of space. So it looks like volume doesn't depend on the single particle. Pressure, temperature, that's probably better, easier to find. So let's try to find pressure and temperature as a function of this data that I have here. That shouldn't be too difficult. Okay, definition of pressure. Who knows? What? 1 atm. No. How do you define something divided by something or something multiplied by something? Force divided by area. Okay, let's call it A for area. Good. I see a problem with this one. Force is a vector, area is a scalar, pressure is vector? No. What's wrong with this definition? If it's vector on one side, it must be vector on other, or if this is not vector here, it cannot be vector here. All right. The point is that there are no vector on both sides, and instead of taking the force, you are just taking the force perpendicular to A. Saying in other words, if you have some surface, A, and you have a force here, vector, then you are just taking this part, that is the force perpendicular to this surface. Okay? So you are not interested in the force vector, but in the force perpendicular one. Good. So we have the first thing. Now we have to calculate what is the pressure. Well, force as a vector, you can define as a derivative of the momentum with respect to time, which is very often written as a just dp over dt. But be careful, this p and this p is not the same. This is pressure, and this one is momentum. And since we have, of course, vector here, there will be vector here. So first thing, we have to learn how to remove this vector. Well, so let's do a model. That wouldn't be so difficult to remove the force. Let's have a cube. Everything we know about this cube has volume V, and it has n particles inside. We also know that the surface of this wall is A. Now we introduce the system of coordinates. Here would be the x-axis, here would be the z-axis, and here would be the y-axis. Good. From this one, I see that the force perpendicular, or maybe it starts again, pressure on the wall A, so pressure in this direction, would be the force in the direction x, that's the perpendicular one, divided by the surface, which would be nothing else like dmvx over dt divided by A. So that's the pressure, but now this pressure is from all possible particles. What I wrote here, it's only change of momentum of one single particle. So I have to write this one multiplied by the number of particles hitting the wall. So what does it mean? I have one particle going, jumping, going the other direction. Another one coming here, going there, jumping. All of them are hitting the wall A. Now everyone that is hitting the wall A is changing the momentum. If I go this direction and later I go this direction, then I change the sign of the momentum to the opposite one. Aha. Let's try to play with this equation. So this is number of particles that hit the wall. Good. This part is change of momentum of a single particle. Good, makes sense. One particle gives some force. Now I have force from all possible particles. Then somebody can say, but this is not true, because I just assume that every particle has the same change of momentum, which is not true. I agree, but then I say this is the average change. Average change of momentum. And now it's kind of okay. This is again not equal sign, but almost equal sign here. If you go to really many particles, this turns to be equal sign. So as you see, even from the beginning, I'm doing a lot of extrapolations or interpolations or assumptions. But here I'm just saying it's almost equal. Okay, now we have to calculate these things. If you just play with this a bit, you find that this is mass of a single particle divided by A dVx dt times number of particles hitting the wall. Okay, first I have to do this thing, dv over dx. Dvx over dt, yes. Well, you know that from mathematics, this is nothing else like limit with epsilon going to 0 of Vx at time plus epsilon minus Vx at time 0 divided by epsilon. This is just definition of derivative. Well, it turns out that this is the derivative, definition of the derivative with the plus sign. There is another derivation . With the minus sign. This is so-called right derivative, left derivative, and they must be equal. So people very often write these two conditions together, and when you write these two conditions together, then you have this is more accurate. But now we should understand what is the change of momentum in this particle. Well, if you think about that, this one can be also extrapolated as a change of Vx over change of time. And of course there is no equal sign here anymore, there is almost equal sign. Now, what is the change of the average speed? The molecule is going here, and after hitting the wall, it's going in opposite direction. Now, we assume that the heating doesn't change energy. So the energy, kinetic energy, is the same. It means this speed and this speed must be the same. So change of Vx is 2 Vx over delta t. And this one is coming from the fact that we have Vx minus Vx, which gives 2Vx. Okay, so we approximated this one. M over A times 2Vx delta t. And we still don't know what is the number of particles in this volume. Well, number of particles that are going to hit the wall, that would be difficult. Let's assume that we have some short time delta t, and we want to calculate how many particles hit the wall. That wouldn't be so difficult. It's enough to take here the length delta t multiplied by the average speed x. So now we can set up the equation saying the total number of particles inside this volume number of particles inside there, that I call it n tilde, divided to the total number of particles is the volume of this something divided by the total volume. But volume of this something is nothing else like Vx times delta t times A. So from this one, I find the number of particles in the red one, that I denote like that, is equal to the total number of particles multiplied by Vx delta t times A divided by V. Okay, nice. So I have the number of particles in this part. And now I want to know how many particles hit the wall. If this is so, maybe I put double tilde here. Double tilde. Yeah. Now, I want to know how many particles hit the wall. All of them have the average speed Vx. But the Vx, they can be this direction or they can be this direction. So only half of those particles will hit the wall because the other one will go the other direction and they never hit the wall. So it's 1 over 2 n Vx delta t A divided by V. Now I plug this one to this equation and I find m times 2 Vx divided by A times delta t times 2 times V times n times Vx times delta t times A. That's my new equation for pressure, and I see that fortunately many things here simplifies. This one simplifies, this one simplifies, 2 simplifies. So the final answer is becoming a bit simpler. It's just m n Vx square divided by volume. So coming now here, I need 2 more minutes to work with these equations. What I found is that P is equal to V M N Vx square. This is nice. But I want to play with this one a bit. First, I don't like the mass of a single particle, so I'm changing this one to the number of moles times the molar mass. That's the mass of a single particle, the total mass, sorry, times n times Vx square divided by V. Total mass. No. This was a mass of a single particle. Sorry, this equation is wrong. I have to write it in the correct form. Mass of a single particle and number of particles. Yes. Should be mass of a single particle. I changed this one. Number of particles is number of moles multiplied by the number of particles in 1 mole. So Avogadro number. Vx square over V. Let's go further. Now, number of particles in 1 mole multiply the mass of 1 particle gives me together molar mass. Molar mass times number of moles Vx square divided by V. Now next thing, I have that V vector is Vx, Vy, and Vz. Now in this big box, particles are going all possible directions. So I can assume that Vx is similar to Vy is similar to Vz. If this is true, then I'm finding that V square is equal Vx square plus Vy square plus Vz square. And this is equal to 3 times, almost approximately equal to 3 times Vx square. Because they are almost the same. The direction doesn't play any role. Then from this one I'm finding that Vx is 1/3 over V square. So total speed of any particles in this box. Then I can plug this one here. And I'm finding that m times n times average speed divided by 3v is equal pressure. That's an important equation. And now I'm going to play with this equation for a moment longer to get 2 important formulas. First, I'm multiplying by V. Then I'm getting PV is equal 1/3 mass, number of moles, times average speed of particle squared. But I also know that PV is nothing else like nRT. If this is true, then I have nRT equal 1/3 nmv square. So I have RT equal 1/3 mv square. Then I'm finding that the temperature is equal to m over 3r times average speed square. So I found temperature as a function of the speed. of particles inside? Well, I can invert this relationship, and what I can find is that average speed is equal to the square root of 3RT divided by m. And these are the important equations coming from this derivation. So just the last look. The particles are going to have large speed if the temperature will be high. Normal. Kind of expected. The particles are going to have large speed if the mass, molar mass of the particles will be small. Also kind of expected. Hydrogen will be moving fast, while nitrogen will be moving slower at the same temperature. Thank you for today.